Hey, welcome back to part 2 of the data analysis tool package, the descriptive statistics tool of the data analysis package. So in my previous video, I discussed at length the mean, median, mode, standard sample variance, range, and standard deviation. And in this video, I want to take some time to discuss kurtosis and skewness. Now, the first thing we'll talk about is skewness. So as you can see here, I have this paper that I got off the internet, and it is by Diva Jane, Skew and Kurtosis, two important statistics terms you need to know in data science. And she has these nice graphs here to demonstrate the different types of skew. Of course, the middle one is perfectly symmetric, looks like a Bell distribution. On the left here, we see a distribution where the mode is more on the left, and we got a tail that kind of pulls towards the right. So you see that the mean is greater than the mode. Traditionally, there also would say, or it was also assumed, that the mean would be greater than the median, and that was the original definition of this positive skew. But with the definition now, the mathematical definition, it is not necessarily true that the mean will be greater than the median, but it will always be true that the mean is greater than the mode when you have this right skew, which is also called a positive skew. So you can think of a number line where it's reaching towards the right where the positive numbers are, so it's a positive skew. Or since the mean is to the right, the mean is bigger than the mode, then the mean minus mode would be a positive skew. On the other hand, we have our negative skew here. And this, you see, the mean is to the left of the mode or less than the mode, so that the mode is on the right, the mean is to the left of the mode, and we got this tail that's kind of being pulled and stretching the distribution out towards the left. On a number line, it would be towards the negative numbers, hence it's a negative skew. So here we have a negative skew, also called a left skew. And over here, when the tail's being pulled towards the right, we have a positive skew, also called a right skew. If you look over here at our data analysis output, our summary statistics, we show a skewness very slightly negative, but almost, really tiny, 0.08. This would actually be considered relatively symmetric. Relatively symmetric. And actually, the rule of thumb is that anything with the skewness between negative 0.5 and positive 0.5 would be considered relatively symmetric. So anything between negative 0.5 and positive 0.5 is relatively symmetric. Another thing is when it's relatively symmetric, your mean, your median, and your mode, in other words, all your measures of central tendency, will be close together. So a data set is considered relatively symmetric when the coefficient of skewness, which is what we have in our output labeled skewness, is between a negative 0.5 and a positive 0.5. And when the measures of central tendency oops, what happened here? Let me fix this. You have to put a space there. And when the measures of central tendency are close to one another. So that is relatively symmetric, the definition. When you have a coefficient of skewness between negative 0.5 and positive 0.5, and that will also correspond to your mean, median, and mode, or your three primary measures of central tendency being close together. And notice here they're all within 1 unit of 2500. So when is something less skewed or moderately left skewed? Let me come over here and talk more about skewness. Right? So we say that a distribution is considered moderately left or negatively skewed when the coefficient of skewness is between -1 and -0.5. This is moderately left skewed. I should change this to not negatively. It is moderately left or negative skewed. No, I guess negatively works. All right. Okay, so you might deduce when a distribution is less than a -1, it is considered very left skewed. So when a distribution is less than -1, it is considered very left skewed. So similarly, we have a distribution is considered moderately right skewed when the coefficient of skewness is between positive 0.5 and positive 1. And it is considered very left skewed. I'm sorry, right skewed. When the coefficient of skewness is greater than 1. All right, so a distribution is relatively symmetric when the coefficient of skewness is between -0.5 and positive 0.5, which also means that the three primary measures of central tendency are close together. A distribution is considered moderately left skewed when the coefficient of skewness is between -1 and -0.5, and if the skewness is less than -1, it is considered very left skewed. Similarly, when a distribution is moderately right skewed, the coefficient of skewness is between positive 0.5 and 1, and it is considered very right skewed when the coefficient of skewness is greater than 1. So that is skewness. Well, there was this other thing called kurtosis. What is kurtosis? When you Google kurtosis, the most likely definition you will get is the peakedness of the data. Peakedness. Now, the article I found, though, has what I consider a much better definition. It's not so much the peakedness of the data as how flat or steep it is, but it is more a measure of outliers, okay? So it's not the peakedness or flatness, it's a measure of outliers. Now, the way she words things a little different than I would. So I'm just going to show you the pictures and explain how I see it, and we'll compare that to how she describes it down here. But let's start by looking at this middle, the moderately kurtic, okay, the one with moderate kurtosis, or called mesokurtic, where meso means basically middle. So when which means middle, that's you see when you got this middle curve here. Now, this middle curve is actually the normal distribution. And it is considered to have a kurtosis of 3. So a kurtosis of 3 is normal. So if you have a measure of kurtosis very close to 3, it'd be very close to normal. However, if you have a kurtosis that is greater than 3, you end up with a tall, skinny distribution called leptokurtic. Leptokurtic kurtosis greater than 3. Here is where she describes differently than I would. She's all the distribution is longer, tails are fatter. Well, I would say the distribution is skinnier and steeper. And so when I look at the whole thing, including the tails, I would see very skinny tails, very short, skinny tails. Remember, the area under the curve has to equal 1, so it has very skinny tails. There's not much going on out here, right? Most of the data is very close together to the middle. That means there is going to be a lot of outliers out here because most of the data is in the middle. So she says a profusion of outliers, right? Peak is higher and sharper, profusion of outliers. I think of it as skinny tails because they're way skinny on the outsides. She says the data are heavily tailed, and I've been thinking about that. And I think it's because, notice, she hasn't really drawn what I consider the tails. And so if you're looking at the ends here, right, you're very thick on the edges there. Whereas if you look at the normal distribution, okay, they're thinner when you look at what she's considering the tails here. I draw the tails way out there so it looks a little differently. So for me, a normal distribution would be something, more like that. It's hard for me to draw it very well. Okay, then we have what she calls platykurtic. Platykurtic, or not what she calls, what is called platy. Platy means flat, right? Duck-billed platypus, got that flat face, flat tail. Okay, platykurtic is when the kurtosis is less than 3. Distribution is shorter. So now we're looking at something that is really spread out like this. Notice it kind of, relative to everything else, it's barely got a bump. So here the tails are what I would consider thicker when you're looking way at the extremes relative to the other two. So where is her platy? There it is, right? So way over here. So see, it's really flat, right? And so compared to these, the tails are, shorter. And so this is what she means by the thinner tails. The way I like to think of it, though, if all the area here has to equal 1 and you're looking far out here, you actually would have what I consider the thicker tails relative to itself. So the difference here is how you define your tails. I define the tails as the outward parts, and I'm comparing it to the rest of its own distribution. So when you're platykurtic, the tails are thick relative to the entire distribution. When she looks at it, compared to the others, and the way she's looking at her tails, they're actually thinner compared to the others. And she's not as far out to on the sides as I be when I think about it. So whichever explanation makes more sense to you, that's what you would use to remember these. So platykurtic, it's flat, which means the data is really spread out. So to be an outlier, since it's already spread out, to be an outlier, you have to be way out there. So that means you are going to have basically no outliers, or very few, a lack of outliers. Normal distribution, okay, we say outliers are about more than 3 standard deviations from the mean. And then the leptokurtic, it's all steep and pointed. So most of everything's close together. So it doesn't take much to be considered away from the rest of the data and therefore have a profusion of outliers. Now it's best when your data is closer to normal so you do not have a profusion of outliers. But of course, that's not always going to be the case. Now, if we look at our example here, so if we go back to our kurtosis, look at that, very small, much less than 3. We're looking at something flat. So this is platykurtotic. Okay, platykurtotic, because it's flat and you will have basically few or no outliers on this one. All right, so not kurtotic, it's platykurtic, my mistake. So platykurtic is a flat distribution, few or no outliers. And I already showed the others, but for completeness, I can put it here, write it out for you guys in these notes. You can at least see it. So kurtosis, normal distribution is called mesokurtic. Kurtosis equals 3. Tall, skinny, so small variation will have many outliers. Its kurtosis is greater than 3, and it's called leptokurtic. Then we have short, flat, few or no outliers. Since has large variation. Kurtosis, less than 3, and that is called platykurtic. So those are the official names or words and the descriptions for kurtosis. So if you want to know, is your data set close to normal? Well, it should have a skewness close to 0 and a kurtosis close to 3. Here, what we have is a relatively symmetric distribution, but it's pretty flat and wide. If we want to actually get more of a visual on this, then we can construct what is called a histogram and or a box plot. So I'm going to show you how to do these because these are tools that I hadn't seen before in some of the older versions of Excel, so I'm not sure when they actually got added. But if we go to data, not data, we need to first, it's going to be a chart. So we're going to be inserting a chart, and it's actually going to be this one here that's in blue, insert statistics chart. So this one up here, which if you see my other videos I've used before to make probability histograms where we have a column chart. We even used it for vertical bar charts, or you got the horizontal bar charts there. But on this one here, where we have our statistical charts, it will create a histogram for you without your actually having to go to defining all the classes that I actually show in some other videos that I made longer ago, and your box plots too. What you need to do though, before you can do these, is highlight your data. So I'm going to highlight the data, and actually can highlight even the label. So I highlight and I insert one of these statistical charts, and let's do a histogram. So we can see it's fairly symmetric. I'm going to write here histogram, right? Fairly symmetric. It divided it into 4 classes. So Excel divided this up into 4 classes, which are mutually exclusive subdivisions of the data and of equal size, equal width. And we see how the data is mostly in the middle here, and then we do have these thick tails, so it has, you know, this relatively short, flat shape, right? If we were to draw it, we see, yeah, this looks relatively short and flat, because if we were going to extend it, it would be a while till we got to, you know, the horizontal axis here. So it's really thick out here. However, the tails are relatively thin compared to the entire height of the distribution. So we have a platykurtic distribution. What about the box plot? What will that show? Let's highlight the data again. So I click out of here. Let's go up, highlight the data again, insert, go to the statistical charts, but this time we pick a box plot. Here they're calling it box and whisker. So you can call it box plot or box and whisker, because here is the box and here are the whiskers. Now notice how we got these bars that end. There are no outline points. There are no outliers on this. Again, we can see this looks pretty short, fat, okay, not super long whiskers. If we hold this here, we can see, notice if, let me see if I can get my pencil back. So 2510, the maximum's 2509.5, very close, and we can see how close it is to that. So the maximum here, 2509.5, I have to turn that off. When I hold this just right, yeah, you see how you can see it says 2509.5. So that is the maximum. What's in here are the top quarter, top 25% of the data, the largest 25% of the data. So here is the top 25% of the data. Okay, so this is the top 25%. Down here, we have the bottom 25%. This one's our max up here. This is our min right here. Okay, this right here. And remember the difference between the max and the min, right? That difference is your range. So what's going on in the middle here? Well, this middle part right here, that's the middle 50%. So here is the middle 50%. And that is called the interquartile range. Having some difficulty writing that way, so let me write out here. The interquartile range. And the interquartile range is the difference, does that work? It's the difference between the the third quartile and the first quartile. So right here, this is what we call Q3, which is the same thing as the 75th percentile, right? It's the same as the 75th percentile. Down here, or at the bottom of the box, notice 25% of the data is below it. This here is the middle 50%, right? So we got 75% below it. Here there's only 25. This is Q1, which is the 25th percentile, or P25, right? 25th percentile, P25. And if I hold the cursor in here, notice 2499.895, you might recognize that when it's right on the X. This is the one on the X. That is the mean. So the X represents the mean, okay? This X here, so this X, that is the mean. But this vertical line here, that is the median. Okay, that one's the median, which is the same thing as, you might guess, 1, 3, that must be Q2. It's also the 50th percentile. Median is the most common word. And if I can get my cursor in the right place, oh, it didn't go away. If I get my cursor in the right place, it should show, see the 2500.1, you might recall that was the median. And when I point that, that's to 2499.895, that is the mean. So what do we have here? Max, Q3, median, Q1, minimum. Those are referred to as the 5-number summary. That's the 5-number summary. Q3 is an upper quartile, Q1 the lower quartile. So this then here is a box plot, and you get a lot of information from it. Let me up here write box plot. Usually it's 2 words. Okay, so there's the box plot. Let me click on here again, and so the chart tools come up when I'm clicked into the chart. And when I go to design, there is a layout somewhere. Let's look at these different layouts. Here it is. Yeah. So I'll click on this, and I will clear all my writing and see what we have here. We have the max written right there, the min right there. Here is the mean, median, upper quartile Q3, lower quartile Q1. 1, 2, 3, 4, 5, 5-number summary. If you had a leptokurtic, if you had a leptokurtic, this is platykurtic. If you had a leptokurtic distribution, what you would have is these whiskers here would be much longer relative to the middle. They would actually end before you hit the least and greatest values because you would have outliers. So they would end, and then you would see points out here showing the outliers. And the way they determine then where it ends and what's an outlier is this interquartile range. If you're more than 2.5 times that, you get an upper fence. Less than 2.5 times that distance, you get a lower fence. So anything beyond 2.5 times this interquartile range is an outlier. So interquartile range, anything more than 2.5 times the length of the interquartile range is considered an outlier, right? and the actual 2.5 times, so 2.5 times interquartile range plus that upper quartile Q3 equals the upper fence, 2.5 times the interquartile range, okay, subtracted from the lower quartile Q1, that gives you the lower fence. Anything beyond those fences are outliers, right? Interquartile range, mean, median, upper quartile Q3, lower quartile Q1. So a box plot gives you a lot of information. It's part of what's usually referred to as exploratory data analysis, one of those things you would like to do early on. You got your data, you get all the summary statistics we talked about before over here, right? All these summary statistics. We're studying the data. Is it symmetric? Is it platy or leptokurtic or even mesokurtic, looking close to a normal distribution? And we can get this nice box plot to tell us about that. So box plots are really nice, okay? So that explains skewness, kurtosis, and outliers, the box plot and the 5-number summary. There's just a couple things left I want to show you then related to the summary statistics. I already discussed the symmetry. Now, we were talking about percentiles, so let me show you how you can find those on the data set using an Excel formula. So to get P25, which remember is the same thing as Q1, there are 2 ways. You can actually go to quartile and quartile exclusive. I use the exclusives because, like, when you're using the quartile or percentile exclusive, the highest it can be is P99. And I like to think of percentiles, 100 equal pieces, bottom 1% below P1, bottom 99% below P99. So if you want 99 as your largest percentile, you're working with this EXC after the dot. So quartile exclusive, the array is our data set. So A1 colon A41. And the quartile, this one is the first quartile. So we just put a 1 in there, I believe. Yes. And there we go. There's that 2496.95. The other way you could do it is using the percentile. So if you use the percentile exclusive.exe, same thing, array A1 colon A41, comma, 0.25 though, all right, for K. K is a percentage, so you have to point the 0.25, right, and there you get the same thing. If we do P75, which is the same thing as Q3, the upper quartile, again, we have the 2 different ways. We can do quartile exclusive, A1 colon A41, comma, and then the quartile here is, oh, look, this pops up. This makes it easier. It's the third quartile. There's the 2502.5. We can also do it literally as the 75th percentile. So A1 colon A41. We could type 0.75, but it will also work if you type 75%. If you put the percent symbol, it will read it like a decimal and work just as well. So that's how you can find percentiles and quartiles using formulas. So you can use the percentile, or you can even use the quartile, or array, whoops, is the data set. Okay, and this time though they want to know the quartile, so they just put quart. Interquartile range, I told you, was the difference between P75 and P25. We can compute that here. So P75 minus P25, and our interquartile range is 5.55. Coefficient of variation. This is the last thing we'll talk about relating to the data analysis tool and our summary statistics before we move on to confidence intervals. A coefficient of variation is a ratio of the standard deviation to the mean. Why yet another measure of variation? Well, the standard deviation is in the same units as the mean, so for us these are both PSI, PSI. The units therefore cancel, and what you have then is a unitless measure of variation. Unitless. And then you can multiply it by 100 to get a percentage. So a percentage then that describes the variation. It's just the internal variation. And then you can use this to compare data sets with different units, right? So that's really useful to compare different types of data sets to make them comparable when they have different units especially. So the coefficient of variation. And the coefficient of variation, like I said, is simply the standard deviation divided by the mean. So let's just shoot on over here to our output. So the standard deviation is the measure of variation we want. Standard deviation, there it is right there, divided by the mean. Make sure you click on the mean and not the median. All right, there we are there. And we get zoom 0.00194. Notice that is just 0.194%. 0.194%. So relatively speaking, even though we're like it's short and flat, and that means it's got a large variation, right, and no outliers, when you kind of think of its internal variation relative to the size of the standard deviation to the mean, not just saying, oh, it's a big standard deviation, but measuring it relative to the value of the mean, we see it's actually a very small variation when we use the coefficient of variation. So again, a very, very useful measure of variation that's unitless, and it takes into account like the scale of measurement that you're using. So not only does it get rid of the units, but as in the scale of measurement, are we talking really big scales or really small fractions kind of thing? And so the relative ratio of these can make a big difference. That then concludes my discussion of the data analysis tool, the data analysis package, descriptive statistics tool, the summary statistics output, and what it all means. The only thing I didn't get to is the confidence level here last, and I will talk about that in the next video titled Confidence Intervals for Means. So I hope you watched that, and I hope this video was very useful. Thank you for watching.